Today I'm going to talk about XPath. It's a joint work with Shuihai, Wang, and Hao in Hong Kong University, my students, and my collaborators, Haitao and Chuanxiong from Microsoft, and Chang from UC Berkeley, and Hongze from Duke University. So as all of you know that today, driven by modern internet applications and cloud computing services, data centers are being built around the world by big companies like Facebook, Microsoft, and Google. And to increase network bandwidth, so which is a requirement for applications, data centers to increase bandwidth, network bandwidth, and for tolerance. Data centers are usually built with multiple paths between any two nodes. And the current practice to utilize this multipath is through ECMP, which is called equal cost multipath routing. So basically what ECMP does is that each switch locally decides the best path among a few best passes through a hash function of the packet header. As a result, flows will take a randomized inexplicit path across the network. Okay? Due to this reason, actually, previous study showed that on average, which is on average not the worst case, over 60% of net bandwidth wasted due to path collection, especially for those elephant flows. As we show in this example, actually, elephant flows, they can be mapped onto the same path, which cause collision while leave other paths sit idle. So basically, in order to fully utilize the network bandwidth, the prerequisite is that we must be able to explicitly control the end-to-end path. So with the explicit path control, we can map these elephant flows onto different parallel paths to fully utilize the network capacity. Actually, nowadays, the requirement of explicit path control actually is prevalent in new data center applications. In the next few slides, I will introduce several of them. Our first example is provision IOPS, which is a new feature. They were recently launched by like Amazon EBS or Microsoft Azure Premium Storage. The goal is to deliver predictable and high performance predictable performance for IO intensive applications such as the relational database services. So in order to guarantee the provision IOPS, actually we need to, because these workers or these VMs to access the storage through the network. To guarantee the provision IOPS, we must first be able to guarantee the bandwidth. We must be able to provide necessary bandwidth across the network. Actually, explicit path control can choose among multiple passes that the one with necessary bandwidth to make the provision IOPS easier to implement. The second example is network update, which is frequent operations due to normal network management, such as like switch update or triggered by failures. For example, in these operations, actually, the network must, the operator want to make the this network management will not cause, will not affect the normal traffic or cause a consistent congestion. For example, if we want to do the firmware update on this middle switch, actually before we do the network update, we want to shift the path, shift the traffic on the path to another path with enough residual bandwidth to handle the traffic. And after it is completed, we must be able to shift the traffic back to the original path. Actually, explicit path control can make such path shifting due to the network update easy to conduct. The third example is map-reduce applications. As you know, the shuffle stage between map and reduce actually gives much stress to the network because they require even auto communications, which require full bisection bandwidth. Actually, nowadays data center with has multipaths between any two nodes, and the explicit path control can be leveraged to arrange disjoint parallel paths to speed up this data shuffle. Okay. Actually, besides these concrete examples, there are many other cases that explicit path control are very necessary or beneficial. For example, for those traffic engineering, either intra-data center traffic engineering, such as micro TE, or inter-data center traffic engineering, like B4 or SRAM. For flow scheduling or packet scheduling, which like Hedra, which is for flow scheduling, and FastPass, which is for packet scheduling. And even multipath congestion control, network virtualization with bandwidth guarantees, and power saving, and network diagnosis and failure handling, and so on and so forth. All these applications or services, actually, they directly require explicit path control or directly benefit from it. Okay, so as we can see that explicit path control is just prevalent in data center applications. Let's see how this prayer work implement explicit path control. Actually, if you look into this work, most of this work actually leverage OpenFlow to dynamically control the OpenFlow to dynamically control the limited generic and limited OpenFlow entries in OpenFlow switches to dynamically set up the explicit path for end-to-end communications. And with this path, actually, if a packet enters the network, if there is explicit rule in the switch that matches this packet, will go through. The packet will go through. And if not, actually, it involves the central controller to set up the path to the, for this packet. As you can see, actually, this dynamic procedure necessarily involves a dynamic path setup overhead and time, which partially due to the reason that it operates on the generic yet limited flow OpenFlow table, which nowadays can be 1 to 4K. And also, this dynamic procedure require good synchronization mechanism to maintain the consistency. Otherwise, you might need to routing loop or even black holes. Actually, this motivates us to ask a fundamental question. Can we pre-install all the desired paths without dynamic setup of them during runtime? If we can do this, actually, it will be able to enable new service and applications, because the service and service and application can directly use the explicit path, pre-install the explicit path without dynamically set up them. And also, if we can pre-install these paths, actually we can avoid complicated synchronization and inconsistent issue, which we can guarantee loop-free forwarding, and we can guarantee that there is no black holes due to routing problems. And of course, the black holes can be caused by the misbehavior switches, and if we can pre-install this path, actually this can help to locate the black holes. Okay, so in this work, we actually gave a positive answer to this question by introducing XPath, which leverage existing commodity switches to pre-install all the desired paths in the network. And before we go into detail, actually, we want to make it clear that XPath actually all about how to pre-install all the paths. Actually, how to use this pre-install path is our ongoing work, which is beyond the scope of this talk. And on top of XPath, we can use centralized central controller through like OpenFlow protocols or other custom design protocols to select the paths. This is centralized control. Actually, each end host can distributedly choose whichever path they want to use for their applications. Next, we talk about the XPath basic idea. Actually, the key motivation that motivates XPath design is that we observe the IP LPM table, longest prefix matching table, in existing commodity switches is becoming very large. For example, the Broadcom Trident 2 which is a commodity switch chip, can support 144K IP LPM table. And based on this observation, our natural idea of XPath is that can we leverage IP LPM table to implement explicit path control? So based on this, actually, we can use one simple sentence to describe XPath. Actually, it is explicitly identify a path with a path ID and pre-install all these path IDs, use IP LPM table of existing commodity switches. Although the idea seems simple, actually, in design of XPath, it has several challenges. The first question is that there are many paths in the network, but what paths to consider in XPath? Actually, it's true that we by no means be able to enumerate all the possible paths because it's exponential. Fortunately, in our design, we observed that actually those existing data centers, most existing data centers, actually, they have desired paths in the network, which is not all the optimal, all the possible paths. For example, in fat tree, actually there are for fat tree built with K port switches, there are K square over 4 parallel paths between any two TORs. And in N-layer B-cube network, actually there are N+1 paths between any two servers. And all these paths actually, they can explore topology redundancy they can fully explore the topology redundancy for high bandwidth and for tolerance. Let's take a look at a concrete example. This is a fat tree topology. Actually, over this fat tree topology, there are desired paths like this. Actually, if two servers are located within a rack, the path will go through the TOR. If they are within a port, actually they go through a aggregation switch. And two hosts located in different ports, actually they go through one of the co-switch. Actually, it's undesirable to have a path that has many values, right? These are the desired paths and undesired paths in a fat tree topology. Actually, this actually applied to other other data center topology like Layer-2, B-cube, and HyperX, and so on. So back to the challenge. Actually, XPath, in the first step of XPath, actually, we do not intend to pre-install all the possible paths. Instead, we pre-install all these desired paths. Okay, even though actually there's another challenging question is how to pre-install these desired paths, because the number of desired paths is very large. For example, in a fat tree with built with 64-port switches, there are actually 2 to the power of 32, over 2 to the power of 32 paths between TORs. Even a 32-bit IP address cannot express all these paths. Okay, so in our design, actually, we observe that data center networks usually under synchronized and is operated by a single organization. So we can have centralized control. We can have control of the network. So we design a 2-step compression algorithm to pre-install these desired paths. our two-step compression algorithm have very clear goals. In the first step, we actually aggregate paths to path set, which the goal is to reduce the number of unique paths in the network. Because as we said, the number of unique paths even can exceed the IP address, right? What the number of addresses in the IP address. And for this, actually, we observe that if two paths they are disjoint or they are convergent, they can use a single path ID to express them, because this will not cause any routing ambiguity. Otherwise, actually, on the other hand, divergent paths, if two paths they diverge from one switch, we cannot use a path ID to express them, because this will cause routing ambiguity. This is the first step. And the second step, even after path-to-path ID, path set, actually the number of path set in the network is also very large. It can exceed 144K, which cannot be held flatly by the IP LPM table. So we are in the next step, we compress the prefix. Basically, we assign path IDs to this path set in a way that the path ID can beneficial the prefix aggregation. Okay. For example, in this table, actually we have a set of path IDs. A good path ID can lead to a concise routing table through prefix aggregation, while a bad ID assignment can cannot lead to a concise routing table. Actually, the step 2 is change part of our two-step algorithm. I will use another slide to describe the problem. Actually, the path aggregation, the path to path ID, the path set to prefix aggregation is simple for us if the network has if for a single switch, because we only need to assign those passes that goes through a single port with consecutive IDs that we can achieve optimal solution. However, a data center can have many switches. So a good path ID assignment on one switch can lead to a very bad result on another. For example, in the graph, the bottom graph, a good path ID assignment on the first switch is that these three passes, they need to be assigned consecutive IDs. However, with consecutive IDs, it will cause problems. It causes problems with the second switch, because these three passes that goes through different ports. To solve this problem, actually, we designed coordinated path ID assignment. Basically, the idea is that we first assign IDs to path sets on each switch individually, which may lead to optimal solution, optimal result, but it will cause inconsistent problem, because one path can have different IDs on different switches. And in the second step, we incrementally correct this path ID inconsistency. Okay, and I will skip the details of the algorithm. And in our paper, we have a detailed description of this algorithm. But in this design, actually, we found that we want to clarify that actually this algorithm is designed for generic topologies like those B-cube, like half-X, and so on. Actually, if we only work on the tree, multi-root level tree topology like fat tree and VL2, we even have better solutions that can lead to good, better results. So next, we evaluate the scalability of XPath. Actually, we evaluate XPath on the 4 well-known data center topologies with different scales. Actually, our results show that even with very large data centers, where XPath can still manage to pre-install all the desired paths into IP LPM tables. Actually, if we use like customized tree-based algorithm, we can achieve even better result for fat tree and VL2. And finally, actually, we evaluate we showcase the utility of XPath in several data center applications. In the first experiment, actually, we use XPath in provision IOPS. In this experiment, we try to copy 30 files from X to Y with a provision IOPS of 15K. And with each part check size, with check size being 4K, this 15K IOPS translate to 500 megabit per second level bandwidth. And in this experiment, we show that with XPath, we can provision the necessary 500 megabit per second bandwidth to ensure the provision IOPS. As you can see that with XPath, we can achieve over 15K, around 15K IOPS, while with ECMP, we only achieve less than 5,000 IOPS. So basically, this is the first example. And in the second example, we leverage XPath to assist the network to accomplish congestion-free network updates. And in this experiment, in order to achieve this, we first actually we want to upgrade the switch on A1. And in order to do that, we first shift the traffic on A1 to a path we first shift the traffic on flow 2 actually onto path 3 in order to set aside available bandwidth for the traffic on A1. And next we shift the traffic of F1 the flow 1 to path 2. And after the after the switch update, we shift the traffic back to the original path. Basically, we measure the path, the throughput at each path, during this procedure, and we didn't see with XPath, we didn't see persistent network congestion. And in the first example, experiment, actually, we leverage XPath to accurately enforce virtual data center VDC with bandwidth guarantees. And I will skip the details of this experiment that basically show that with XPath we can accurately we can accurately do the VDC embedding. So in the first first example, actually we use XPath to speed up the data shuffle of memory reduced applications significantly. And this is a related work. So basically, we just skip the details, and we have detailed description of related work of XPath. To summarize, actually, in terms of design, XPath has a very simple concept based on a very simple concept of path ID to express the end-to-end path, and then have an idea of pre-installing all design paths into IP LPM tables, and we leverage a two-step compression algorithm to translate idea into practice. And in terms of application, XPath is very scalable, work on very large data centers, and it's practical because it's easy to implement. We require no modification on commodity switches. We can incorporate XPath into many applications and directly benefit them. And all our other projects in our group actually heavily rely on XPath to do the experiment implementation. With this, our implementation and the description of XPath actually is online available through this website. We are encouraged to try them if you need. Thank you.
Questions? Please.
Hi, I'm Edward Tremmel from Cornell University, and I realized that in order for you to describe that experiment where you have the switch that needs to be upgraded and the traffic rerouted, that involves explicitly choosing between paths. But I thought you started out by saying that we're only going to talk about how to install paths, and we haven't actually implemented the algorithm for choosing between the paths once they're installed. So how did you get that to work?
I'm sorry, can you repeat the last part of the question?
I wondered how you got that experiment to work, because it seems to require explicitly choosing between paths and changing live traffic from one path to another, and all you described was how you installed the paths.
Right. So basically, the experiment to show that we try to compare explicit path control with implicit path control like ECMP. So basically, that experiment is that we assume we know the knowledge and we have XPath as explicit path control. We can manage to upgrade the network without consistent without persistent congestion. While with ECMP, actually, we cannot achieve that.
Right, but does that experiment sort of assume something that hasn't been implemented yet? Namely,
Right.
a way to choose between the paths that you've installed with XPath?
Yes.
Okay.
Any other questions? So while we're waiting for the setup, I have one quick question. So if you, it seems like you assume that you won't change the ID or path ID inside the network while the packets are being forwarded. If you allow that, I mean, if you allow the identifiers to be rewritten by the individual hops, would it change your figure, very much differently, or what do you expect to gain out of that kind of approach?
Actually, we do not change. So basically, best ID, basically the first step in the first hops on there is the end host or the first hop TOR switch. It will decide a path ID, and that path ID will not be changed across across the entire path.
But if you decide to allow the path ID changes by the switches, would it say, for example, host a lot more path, or do you have some insight into that scheme?
So actually, in our design, we once the path D is pre-installed, we do not allow them to be changed.
Yep.
Yes. If so.
Okay, I wanted to understand the other side of I wanted to understand your view on the other side of the approach, but I think we can take this offline.
Okay.
Okay. Right.